We're going to get real into the notion of displacement, velocity, and acceleration by just looking at one example and really picking apart this graph in as much detail as we can, just using first and second derivatives. So a particle moves back and forth along a straight line. So you have to picture it just zipping back and forth along like a fixed track. We don't really have the tools to do a particle zipping around on like a plane or something because you need parametric curves. Okay, so it's just moving back and forth like a train. Its displacement at time t is given by this thing. S is t cubed minus 12t squared plus 36t. So there's the graph of its displacement, but remember it's not moving up and down, it's just moving back and forth. So it starts off at time 0 at position 0. It starts moving to the right, and then it looks like at t equals 2 seconds, it moves back. So it moves back to its original position, turns around again, and then it looks like it just shoots off to the right forever. So we're going to use the derivatives and pick stuff apart to actually show exactly what happens. So part A is just to find a function for the particle's velocity, which we all know how to do that at this point. It's just the derivative. V of t is s prime of t. That derivative is child's play at this point compared to what we've been doing, right? Very easy derivative. So there's the velocity. And there's the graph. So, right, it lines up with what we suspect. At time 2, the velocity is 0, and at time 6, the velocity is 0. That means it's essentially stopped at time 2 and time 6 because that's when it's turning around. The fact that the two graphs intersect right at 6 doesn't really mean anything. That's just kind of a coincidence. So to actually show that, we have to do some math, and we've done this before. So it's at rest when v of t equals 0, so we have to solve an equation. Just good factoring skills, factor out a constant if you can, and then factor what's inside there. So it's 3, you can get rid of the 3 because you just divide it out. So it factors to t minus 2 times t minus 6, which is what we suspect. So it's good to be able to look at the graph and see what's happening. This just proves that's what's happening. So again, you can see when it's moving in the positive direction just by looking at the original graph. When the graph is going up, we consider the graph increasing corresponding with moving right or the positive direction. That's right, yes. But in particular, it's whenever the derivative is positive. So whenever that red curve v of t is positive, the particle is moving in the positive direction. So in other words, wherever it's above the x-axis. So you can do the algebra to solve like a polynomial inequality, but I wouldn't make you. I would just say use the graph. So you can just look at it and see that, okay, from time 0 to time 2, that red graph is above the x-axis. And from time 6 to infinity, that red graph is going to be above the x-axis because it's a parabola. Okay, so you're welcome just to use the graph for that. You found the intercepts algebraically. They intercept at 2 and 6, so you know it's switching at those points. So all you have to do is look at it, and oh, it's a right side up parabola. Okay, so it's between 0 and 2, and then anytime after 6. Same thing if I ask when it's moving in the negative direction. It's just whenever that parabola dips below the x-axis, and that's just between time 2 and time 6, and that covers everything because it's only moving one way or the other. We know that this thing's acceleration is just the second derivative. So you just take the velocity and take the derivative again. Velocity is change in position. Acceleration is change in velocity. All right, so again, super easy derivative. It's just 6t minus 24. So right, the graph of a cubic was a quadratic, and the derivative of a cubic was a quadratic, and the derivative of our quadratic is a linear. That's what it looks like. It's the purple line. It's literally a line. It crosses the x-axis at 4 seconds. That's kind of important, and we'll get more into that in a little bit. Right, so the acceleration is 0 right at time t equals 4 seconds. And you could very easily solve 6t minus 24 equals 0 to get that algebraically. You can probably do it in your head. T is 4. So that becomes important. That's called an inflection point in the graph of f. What it does is right at t equals 4, the graph switches from being what we call concave down to being concave up. We'll get more into that later. That's what the second derivative tells you about the graph. But in this context, that's a moment. So when acceleration is 0 doesn't mean it's stopped. Velocity is 0 means it's stopped. Acceleration being 0 means it's switching from speeding up to slowing down, or vice versa. So it's like the moment when you get on the highway and you're accelerating and accelerating, the moment you take your foot off the gas, at that moment you're not accelerating at all. You're switching from speeding up to slowing down. Right after that, you're decelerating. But at that very moment, your acceleration is 0, so that's what that represents on the graph of the second derivative being 0. So let's talk about how we know when it's speeding up, because that's not as obvious from the graph, but if you think about it, it should be kind of intuitive. So if it starts out at time 0 and starts moving to the right and then stops, it had to slow down to stop. So it seems like it should be slowing down immediately. Like right at time equals 0, it should slow down, slow down, slow down, slow down, stop at time t equals 2, then speed up again. And that's what's happening. But here's how you know that from these graphs. So this is a little more complicated. If the velocity and acceleration are both positive, that means, okay, that's like your car's moving forward and you're being pushed forward. So that means you're speeding up. If the velocity and acceleration are both negative, that also means you're speeding up. The same exact thing is happening, just in the other direction, right? So if the thing's moving backwards and being essentially pulled backwards, it's still speeding up. So you have to use the two graphs. You can't just say, okay, when acceleration is positive, it's speeding up, and when acceleration is negative, it's slowing down. That's not how it works. Velocity and acceleration need to be going in the same direction. So if you just look at the red graph and the purple graph, from time 2 to time 4, they're both negative. And what that means is, in terms of the particle, okay, it stopped at time 2, and then it has to start speeding up again, right? Because it stopped. So it stopped at time 2, it speeds up again until time 4, and then that's where that inflection point happens. And then it starts slowing down again from time 4 to time 6 so that it can stop at time 6. So it's from, we can just go through the whole graph. So if the velocity and acceleration have opposite signs, the particle is slowing down. So from time 0 to time 2, we see velocity is positive, acceleration is negative. That means it's moving in the positive direction, but it's being pulled in the negative direction. So that means it's slowing down, because the red graph is up here and the purple graph is down here. So it starts out going pretty fast and then immediately slows down until time 2, where it stops. Now we have, right between time 2 and time 4, it stopped, so it really has no choice but to speed up. So it speeds up because both the red graph and the purple graph are below the x-axis. So it's speeding up until time 4. And then it switches to slowing down again, which it has to, so that it can stop again at time 6. So between 4 and 6, we have acceleration being positive, velocity being negative. So that means it's moving in the negative direction, but being pulled in the positive direction. So it has to slow down. So after it stops at time 6, again, it has no choice after a stop but to speed up again. So, and the graph bears that out. After t equals 6, the red curve is now above the x-axis, so it's positive, and the purple curve is also positive. So v and a are both positive forever, right? So henceforth, after t equals 6, v and a will always both be positive, so the particle is just going to speed up forever in the positive direction. Okay, So that's how we can use first and second derivatives to get a lot of information out of just a function. That's a lot of information out of that thing. And then again, we can kind of cheat a little bit and just compare the three graphs to really figure out exactly what's going on with this thing at every point in time. In physics, the third derivative is called jerk. So imagine that's like you're on a roller coaster, you slam on your brakes or something. Jerk would be a sudden change in acceleration. Usually in a case like this, acceleration, or a jerk is pretty constant. In fact, the third derivative would just be 6 at this point. We don't get any information from the graph about the third derivative, and we don't even really, in Calc 1, we don't use any derivatives higher than the second one. They do have applications, but we don't need them for now. So these are tricky. This is an application of implicit differentiation. And they're all story problems, your favorite. So we take the fact that we know how fast one thing is changing, and we have this related thing, this related phenomenon, that we can figure out how fast that's changing based on the thing we already know. So we have two quantities that are related. You'll see in a second. One thing is happening at a certain rate. We use that to figure out at which rate the other related thing is happening. So the only way to wrap our heads around this is just to see examples. So I'm just going to show you 3 examples right now. Okay, we have a water tank in the shape of a cylinder and with radius 2 meters, and we're pumping it full of water. And we're controlling how fast the water is coming in. So we're filling it with water at 4 cubic meters per minute. And so we have water coming in, and we want to know, okay, but what about the water level, the actual height of the water in the tank? How fast is that rising? That's what that looks like. So, right, we know the water flow is coming in at 4 cubic meters per minute, and obviously that's making the height of the water rise. And we want to know how fast the height of that water is rising. So if we had something floating on top of that water, how fast would it be moving up? And it almost seems like we don't have enough information to get that, but we do. So the first thing with these is to name stuff. In the next problem, I'll give you a real step-by-step rubric for how to do these problems, because they're all kind of the same. But for now, let's just talk through it. So let's call the water level H for height, and let's call the water volume V. Why not? So that 4 cubic meters per minute, that's volume, right? That's how fast the volume of the water is growing. So we need to put the related in here. Obviously, those two things are related. The faster the water comes in, the faster the level goes up. And we do have an equation because it's just, if you just look at just the water, okay, the water is in the shape of a cylinder, and we certainly have an equation for the volume of that cylinder. If you don't remember equations for volumes of spheres and cylinders and stuff like that, you don't have to memorize those. You'll be given them if you need them. So that's it. That's just the volume of a cylinder. It's pi r squared h. So it's just the area of the top of the cylinder times the height. That's generally the case for all volumes of what we call prisms. And we actually know the radius of the tank here, right? That's really the only other piece of information we were given. So plug that in, right? R is 2. So it's pi times 2 squared h, which can be more eloquently written 4 pi h. So the volume of that water is 4 pi times the height of the water. Okay, so here's the part that's tricky. Now we use calculus. So the volume and the height of the water are both functions, and they're functions of time, right? Time is only progressing in its own linear way, and the volume is increasing over time, and the height is increasing over time. And what do we want in the first place? We want, well, what is that change in the height of the water over time? That should remind you of like h prime. So we want to treat v and h as functions, which they are, and differentiate both sides of this equation. Right? So remember that they are functions. We don't really have a strict rule for the function h because it's changing as some other thing is changing. But we know how that's happening. We know how they're related. So here's an application of implicit differentiation. We're going to use t as the variable, not x, and we're going to differentiate both sides of this thing, keeping in mind that v and h are functions, so things like the chain rule and stuff have to be applied. We don't really need the chain rule here because it's just, okay, one function equals 4 pi times another function. So that's just a constant times it. So, right, what is the derivative with respect to t of v? That's literally what dv dt means. So now this is the first time I've really used this Leibniz notation. So that really means the same thing as v prime. I'm just being a little more specific because I'm saying the change in volume with respect to time. And then you could use h prime instead of dh dt, but I'm just saying that's the rate of change of the water's height with respect to time. And then the derivative of that side, remember 4 pi is just a constant, so it just comes along for the ride. So dv dt equals 4 pi times dh dt. We didn't need the chain rule or anything like that. Now we have to remember what we're even looking for. So we're looking for the rate of change of the water's height. So that's what dh dt is. So the next step is to solve that little equation for dh dt. That's the thing we were asked for in the first place, so you have to know that. That's easy to do. You just divide both sides by 4 pi. So 1 over 4 pi times dv dt equals dh dt. And now the very last step in these is to sub in the thing we know. So if you look at the setup of the problem again, we were told the radius of the tank, and we were only told one other thing. We were told how fast the water was coming in. That's what dv dt is. All right, we were given that the change in the volume of the water with respect to time was 4 cubic meters per minute. So you have to know that, oh, that's what that is. If I tell you it's being pumped in at 4 cubic meters per minute, you have to know, oh, that's dv dt. That's the change in the water's volume over time. So that's a rate, and now we can finally plug that in. There's a danger of plugging this in too early, so we'll make sure and avoid that. So just follow my steps and you'll be fine. So stick that in there. 1 over 4 pi times 4 equals dh dt. Those 4's just so happen to cancel out. So it's 1 over pi. The change in the height of the water with respect to time is 1 over pi. And then as far as the units, I do want to see units, but just think about what the units for this are. Height is a one-dimensional thing, so it's just meters per minute, right? That's just like miles per hour or whatever. That's just the speed of something that's just going one direction. And then with these, I'll usually say round to a couple decimal places, just because 1 over pi, who even knows what that number is? So it's a pretty small number. It's 0.318. So the water's coming in relatively fast, but it's a big tank. So the height is changing very slowly. It's only, well, that'd be what, like 30 centimeters per minute. So 0.318 meters per minute is how fast the water level is going up. Okay, we'll do a couple more of those. I know that seems complicated, but they're all kind of the same. Okay, this is actually almost the same exact type of problem. It's going to shake out in much the same way. I'm just going to break it down a little more step by step and give you a general strategy for these. And then, it's going to be a different function because now we're dealing with a different geometric shape. So the calculus is going to be a little different. So we're pumping up a balloon. It's perfectly spherical. And we're pumping it up at the rate of 100 cubic centimeters per second. So think about right away what that is. What's happening at 100 cubic centimeters per second? That's volume, right? We are changing the volume of the balloon because that's how much air is in there. And now, though, we want to know about the balloon's radius. So So we want to know how fast is the radius of the balloon increasing. So just picture a sphere with a radius at the exact point when the radius is 25 centimeters. So the thing about this problem is if the balloon's small, the radius is increasing pretty fast, but the bigger the balloon gets, it's going to start actually growing slower. Even though we have the same amount of air being pumped in, the radius isn't going to grow as much, as fast. So we're specifically wondering how fast the radius is increasing. At a certain point, that point is when the radius is 25 centimeters. Okay, so here's what I mean. Here's my step-by-step process that works for all of these. Step one, name stuff, right? Keep it simple. V, we're talking about the balloon's volume versus its radius, so just call the radius R and the volume V. And then before you even set it up, it's good to identify what we're even being asked for. When we say how fast is the radius increasing, the quick way to say that is what is dr dt, right? The change in the radius with respect to time, the rate of change of the radius of the balloon. And then say, okay, what is that 100 cubic centimeters a second? That's dv dt. That's volume. That's how the air is coming in. So we know dv dt, we want dr dt. Step three, relate, right? The two things are obviously related, but we need to specifically know how they're related. So the volume of a sphere and the radius of a sphere are related like this. And again, if you didn't remember that equation, don't worry about memorizing it. That's just the volume of a sphere. That's a very old formula. You actually can't prove that until calculus 3. But you've seen it before. So 4/3 pi r cubed is the volume of a sphere in terms of its radius. So that's the equation we're going to be working with. It looks similar to the last one. There's a little more going on. Now we do our differentiation. So we're always going to be differentiating both sides of an equation with respect to t. So the derivative with respect to time of v is literally just dv dt again. So that's all the left side is going to be. But now we have 4/3 pi times a function cubed. And r is a function, so the derivative of r isn't just 3r squared. The derivative of r is 3r squared times r prime, right? Times dr dt. Again, imagine if r were sine of x. The derivative of sine cubed is 3 times sine squared times cosine. So that's the chain rule, right? R is not just a variable, R is a function. So the 4/3 pi just comes along, that's still just a constant, it comes along for the ride. So it's 4/3 pi times chain rule 3r squared times dr dt. If you want to just use v prime and r prime for those things, go for it. I certainly wouldn't mark it wrong. I like to use this Leibniz notation for these. We can simplify that right side a little bit. The 3's cancel out, so it's 4 pi r squared times dr dt. So that's just that last slide copied again. Now, since we already figured out at the beginning what we want. We were asked for dr dt, change in the radius. So solve that little equation for dr dt. That's never going to be the hard part. That's easy. You just divide both sides by 4 pi r squared, and don't worry about the fact that there's still an r in there. Just get dr dt by itself. So 1 over 4 pi r squared dv dt equals dr dt. And then always leave this for the end. This is it. Substitute in what we had at the beginning. So get everything solved for the rate that you want, and then stick in whatever you have. So we were given dv dt. That's how much air is being pumped into the balloon. That's a rate. So that was 100 cubic centimeters per minute or whatever. And then we were given the radius of the balloon. See, in this problem, like the last one, we need to know exactly when we're looking for this rate. So we're just looking for it when at the point when the radius is 25, whatever point that is. So stick both those in. Right. So this is what I was saying. If you stick these in at the beginning, think about if you stick in v equals 100 at the beginning. and then did the derivative. Well, the derivative of 100 is 0. So your whole equation would be like something equals 0. And then hopefully you'd be like, that doesn't seem right. So do not do this until the end. Don't use those numbers until the last step. You can do it anytime after you differentiate, but just don't. Just follow my steps. Okay, so just sticking in 25 for R and 100 for dv dt. That's it. That's the answer. That's dr dt. Obviously, we can clean that up, so some stuff cancels out over on that side. And it simplifies just to 1 over 25 pi. I like units here, and I like decimal places, just so you have some idea of what you actually just did. That turns out to be 0.0217, so obviously use a calculator for that. So pretty tiny, right? So, but that should make sense. When the balloon, 25 radius is a pretty big balloon, so when the balloon's getting pretty big and you're pumping the same amount of air into it, it's really, you're barely going to see the balloon actually growing. It still is, but it's growing, the radius at least is growing very slowly the bigger the sphere is. So it's only about 0.01 centimeters per second. And then for the units, just think about what they should be. It's a radius. Radiuses are measured in centimeters, so it's just centimeters per second. Last one. This is going to be a little bit more complicated of a setup, but it's still just going to be some geometric thing that we differentiate both sides of. We have two cars start driving away from each other at the same point at the same time. One car is going south at 60 miles an hour. And the other one is going west at 25 miles an hour. That's all we know. After 2 hours, so right when t equals 2 hours, at what rate is the distance between the cars increasing? So we know how fast both the cars are going respectively, but what about how far they are apart from each other? So if you're not given a picture with these, you have to draw a picture. How could you possibly wrap your head around this if you don't have a picture? So draw a picture. So we got our picture. We're going to label everything. So that corner of the circle there where the right angle is where the car started from. One car is going directly south and one car is going directly west, right? So that's what that looks like. Let's name some stuff. Let's name car A, the car that's driving west, and car B, the car that's driving south. No reason for that, just got to call them something. We're going to let X be the distance traveled by car A. And now X is changing. X isn't exactly fixed, but that's okay. We're specifically concerned about the moment when 2 hours has passed. Y is just going to be the distance the other car travels, I guess because it's vertical. And then the thing we're concerned about is Z, right? That dotted line is the distance between the two cars. That's the thing we're looking for, how fast it's changing. So you just have to picture this right triangle with both the legs growing, right, at a different rate. And essentially what we're wondering is now how fast is the hypotenuse growing, right? If we completely forget all about cars and stuff, this is just a triangle where the legs are both growing, and we want to know how fast the hypotenuse is growing. Okay, so we want dz dt. We'll worry about exactly what we have a little later. Now we have to relate those three things, and you know how to relate those three things, right? So there's generally some formula from geometry that comes up here, and that's the Pythagorean theorem. So we have the two legs are x and y, and then the hypotenuse is z. So x squared plus y squared equals z squared. That's the equation we're going to be working with. X, y, and z are all functions. So we actually have three functions here. You can call them like x of t, y of t, and z of t if you want. And then we're going to be getting x prime, y prime, and z prime. But they're all, you just think, however you think about it, just think about that they are functions of time because they're changing. So anything that's changing over time is a function. And so when you differentiate a function that's a function squared, you have to use the chain rule. So here we use implicit differentiation. Differentiate both sides with respect to our variable, which is t. So the derivative of a function squared, the derivative of x squared is 2x times dx dt plus 2y times dy dt equals 2z times dz dt. So they all differentiate the same exact way. So we could solve that for dz dt now. We would just divide everything by 2z and then stick in all the information we have. Or we can stick in the information now because I think it's easier because there'll just be a bunch of numbers. So as long as you wait until after the differentiation part to stick in the stuff you were given, it works out fine. And you'll see that. You're just either doing algebra or you're just like plugging in numbers and then doing arithmetic. Okay, so it doesn't seem, well, let's think about what we do have. What is 60 miles an hour? That's the speed at which the car B is traveling, right? So since so that means y is increasing over time, the distance is traveling. So 60 miles an hour is dy dt, right? It's the change over time of that distance. Same with 25 miles an hour is dx dt. That's the rate at which x, that distance x, is changing over time. So we have those two. If you look at that last equation, we have dx dt, we have dy dt. We want dz dt. We don't have x, y, and z, but we can get them. So here's how you get x. We were given a speed. We were given that car A is going 25 miles an hour. And in particular, we were given that we want this rate in question is happening right when t equals 2 hours. So that's just distance equals rate times time. You're going 25 miles an hour for 2 hours. You just went 50 miles, right? That's easy. You can do that in your head. So x is 50, that leg of that triangle. Same thing with y. Just think about it. If you're going 60 miles an hour for 2 hours, y is 120. All right, same deal. So now we have the legs of the triangle. Now we can actually get z. Again, by the Pythagorean theorem. So we're going to actually use the Pythagorean theorem for real now to figure out a hypotenuse. All right, so same deal. Pythagorean theorem says, okay, 50 squared plus 120 squared is z squared. That's pretty easy math. Use a calculator. So z is the square root of 50 squared plus 120 squared, which turns out to be a nice even number, 130 miles. So at this moment, there's 130 miles between the cars. But we don't want that. We want how fast that distance is changing. All right, and then we stick in the stuff we actually were given, is that dx dt is 25 and dy dt is 60. So your job is really just to know that, to translate that. The speed of a car is dx dt, because x is the distance it's traveled, speed is just change in distance over time. Okay, so we plug all that in. So 2 times x times dx dt plus 2 times 120 times dy dt equals 2 times 130 times dz dt. So we just stuck everything in now because now look what we have, just a bunch of numbers and the thing we want. So we just have to clean up those numbers and get dz dt by itself. Okay, so that's mostly just calculator stuff. That's 2,500 plus 14,400 equals 260 times dz dt. 16,900 equals 260 times dz dt, which means that dz dt is 16,900 over 260, which, again, nice even number, is 65 miles an hour. So the distance between the two cars is increasing, obviously, but in particular, it's increasing at a rate of 65 miles per hour. Okay, so those are related rates. Please try examples because there's no way to get good at these things without just doing them. They're all different setups, but the steps of them are always going to be they're going to go down the same way.